Let us now find the derivative dy dx in terms of yx of these three functions y of x that are defined implicitly. Here we know that we need to do implicit differentiation because it says in terms of yx. Otherwise it would be only x. And we also know that it's an implicit function because we have here y mixed up with the x, and we would need to solve for y. The first, we can do that. It may not look good, but it's going to be possible. And the second one is not so easy. And the third is completely impossible to solve for y. You see, because we have the sign of xy and then exponential of y. Okay, so the last one, the only hope here is to use implicit differentiation. So let's go for it. Now would be a good time if you want to pause the video and try by yourselves, then we can discuss the solution. So to do the implicit differentiation, we just need to take the ddx of both sides of the equation, okay? This is always applied to equations. And here, very important, we do ddx to both sides, okay? Don't be lazy and write something like ddx of the equation itself, because this is incorrect. Well, it's I don't like to see this, so don't do this, okay? So ddx of 4 is equal to 0, and then the left-hand side is 2/3 of x to the 2/3 minus 1, so that makes negative 1/3 plus, and here comes the interesting part, ddx of y to the 2/3. Remember, y, this is the most difficult part for most students, y is a function of x, defined implicitly. Okay, so you have to treat it as a function, not a variable. So this will be 2/3 of y to negative 1/3, and then multiply by the derivative of y respect to x. And here we have already what we are looking for. We want to solve for dy dx. So we have 2/3 of negative 1 y to the negative 1/3 dy dx, and this is equal to negative 2/3 of x to the negative 1/3. The 2/3 go, and we have dy dx. This is equal to y divided by x to the 1/3. So I just took the y to the negative 1/3. That's like 1/3 y to the 1/3 dividing, pass it to the other side, and done. So this is the first one. And I'm missing a negative here, so let me fix that. Now it's correct. For the second one, let me copy paste. Again, we do the ddx, x to the power 3 plus y to the power 4 equals ddx 2xy. This is a little different from the previous one, because the previous one, the right-hand side was constant, so we didn't have to do anything with that. Now it's not, so careful there. And here, again, this is problematic for most students, because it's not easy to realize that y here is not a variable, it's a function. So we need to apply the product rule. Okay, this is going to be 2 times, well, ddx of x is equal to 1 times y plus 2x dy dx. And on the left, we have 3x squared plus 4y to the power 3 times dy dx. And now we want to solve for dy dx, which is on both sides. So we need to collect like terms. So this is 4y to the power 3 minus 2x dy dx equals 2y minus 3x squared. And now dy dx, as long as 4y to the power 3 minus 2x is not 0, we can solve for it. And we are done here. Okay, did you notice that so far we have always found the ddx multiplied by something, and it was very easy to solve for it? This is always going to be the case. Okay, there is a deeper reason why it's always simpler to solve for dy dx than solve for y, but that exceeds the scope of this course. Okay, just know that it's easier to solve for dy dx. And the last one, this is going to be a party. The last one, again, we need to take ddx of the sine of xy plus e to the power y equals ddx x to the power 3, which is 3x squared. This one we can do right away. And here we have the sine. So the derivative of the sine of xy by the chain rule is the cosine of xy times the derivative of what is inside. Okay, let's do it in 2 steps. And then the derivative of the exponential of y is e to the y, and then dy dx, because we need to take the derivative of what is inside. And now this is cosine of xy times y plus x dy dx plus e to the power y dy dx. And this is it. So here, let us collect like terms. So this is y cosine of xy plus x cosine of xy plus exponential of y dy dx equals 3x squared. We can pass the y cosine, we can pass the y cosine of xy to the other side, right? There we go. It's a minus. And then just divide by all these things, the x cosine and so on. And this is it. This is the final result. So we were able to find dy dx in terms of x and y for an equation sine of xy plus exponential of y equal x to the power 3, where it's simply impossible to solve explicitly for y. Okay, in this case, we just can't. But we can always solve for dy dx.